Good morning, everyone. Today we are going to discuss about the response of low pass RC circuit for square wave input signal. So this is the square wave input signal we are going to apply to the low pass RC circuit, and this is the corresponding response produced by the circuit. Now it is observed that there is a changes in the input signal at different times. That means at a t is equal to 0, the input signal suddenly increases to the maximum value. That is taken as case 1. And 0 to t1, during this period 0 to t1, the input signal has maximum positive value. That is taken as second case. And at a t is equal to t1, the input signal suddenly decreases to the negative minimum value. That is taken as third case. And between t1 to t2, the input signal has negative value, minimum negative value, that is taken as case 4. Again at t is equal to t2, the input signal suddenly reaches to the maximum positive value. That is taken as the fifth case. That means total number of cases here is 5 cases of operation. First one at t is equal to 0, 0 to t1, at t is equal to t1, t1 to t2, and at t is equal to t2. Total 5 cases. And if you observe that this is a symmetrical square waveform, that means the duration of the positive section is equal to the duration of the negative section, and similarly the amplitude in the positive section is equal to the amplitude in the negative section. The amplitude in the positive section, that is v by 2, that is equal to the amplitude of the negative section with the opposite polarity. And similarly the duration of positive and negative, that is equal to t by 2 and t by 2. Now we are going to apply this waveform to this circuit. Now coming to the first case, at t is equal to t1, the input signal suddenly reaches to the maximum value. Whenever we can apply that signal, this suddenly increasing signal to the circuit, the capacitor is not responded for sudden changes in the input signal. The capacitor is not responded for sudden changes in the input signal. That means simply it does not respond for the input signal, and the output voltage displays the voltage across the capacitor in previous state. Whatever the value which has in the previous state, the same value is appeared across the capacitor, and that voltage is appeared as an output V0. That means initially we can assume that the voltage across the capacitor is taken as V2. Therefore, at a t is equal to 0, when the input signal suddenly increases to the maximum value, the capacitor is not responded for the input signal. It displays the previous value. Therefore, that is taken as V2. That is represented here at a t is equal to 0. Now coming to the second case, that is between 0 to t1, that is this point to this one, the input signal has a constant positive value. Whenever we can apply this constant positive value to the circuit, because of the positive value appears at the input terminals, the capacitor goes into charging condition through a resistor R. The capacitor goes into charging condition through a resistance R. That means the capacitor charges exponentially because the input signal is constant. When the input signal is constant, the capacitor, when the capacitor goes into charging condition, the voltage developed across that capacitor is an exponential motion. That is already proved in step input signal. Therefore, between 0 to t1, the output voltage increases exponentially like this, 0 to t1. So this response is represented with V01. This response is represented with V01. That means initially at t is equal to 0, the voltage across the capacitor is V2. And 0 to t1, the voltage across the capacitor increases exponentially. and it is represented with V01. And at the end of the cycle, that means at the end is equal to T1, the capacitor charges to some maximum value. That value is represented with V dash. That value is represented with V dash. That means during the charging period, the initial value is V2 and the final value is V dash. Initial value is V2 and the final value is V dash. Now coming to the third case, at t is equal to T1, at t is equal to T1, the input signal suddenly decreases to the minimum value. The input signal suddenly decreases to the minimum value. Whenever you can apply this case to the circuit, the capacitor again not responded for the input signal. Therefore, it has the same previous value which is in the same previous state. Therefore, V naught is equal to again V dash at t is equal to T1. Now, coming to the next case, that is between T1 to T2, the input signal has a minimum negative value. The input signal has minimum negative value, that means constant value. Whenever we can apply this negative value to the circuit, the capacitor starts discharging in exponential motion. Because whenever the input signal is constant, the capacitor charges exponentially. In the similar way, whenever the input signal is constant in negative voltage, the capacitor discharges in same exponential motion. Therefore, the output response decays exponentially between T1 to T2. Between T1 to T2. At the end of the period at t is equal to T2, the input signal suddenly increases to the maximum value. That means by the end of this period T1 to T2, the voltage lost by the capacitor is represented with V double dash. The voltage lost by the capacitor is represented with V double dash. That means initially during the discharging period, the voltage across the capacitor is represented with V dash. Finally, the voltage across the capacitor is represented with V double dash. Between these two, the capacitor decreases exponentially. Now, coming to the fifth case, at t is equal to t by 2, again the input signal suddenly increases to the maximum value. Whenever you can apply this signal to the circuit, the capacitor again not responded for the sudden changes in the input signal. It displays the previous stored value. That means same V double dash at t is equal to T2. Finally, we get exponentially charging and exponentially discharging signal for the square wave input for low pass RC circuit. During the charging period, the initial value of the capacitor is T2, final value of the capacitor is V1, and between these two values the capacitor increases exponentially. It is represented with V01. During the discharging period, the initial value is V dash, final value is V double dash, and the discharging motion of the capacitor is represented with exponential waveform, and it is represented with V02. And it is represented with V02. So this is the input signal and this is the corresponding response obtained by the circuit, and this is the low pass RC circuit. Now we are going to derive the mathematical expression for output response of square wave input signal. Now, just now we said that there is a charging portion and there is a discharging portion, and the equation for voltage developed across the capacitor is represented as V01, that means voltage across the capacitor. It is a standard form, that is equal to V final minus V initial into e power minus t by RC. Here V01 represents the charge developed across the capacitor during the interval T0 to T1. Vf represents the final charging value of the capacitor. V initial represents the initial charging value of the capacitor. Here T represents the time period, RC represents the time constant of the circuit. Now from the figure, equation 1 can be rewritten as V01, that is equal to V final is V dash. Final value is V dash. V dash minus V initial is V2 into e power minus t by RC. So this is the rising portion of the output response. Whereas the falling portion of the output response is also represented as the same equation, that is V01 is equal to V final minus V initial into e power minus t by RC. Therefore V02 is equal to, in this falling portion, the initial value is V dash, final value is V double dash. Final value is V double dash, initial value is V dash. Now V final, that is V double dash minus V final, V double dash minus V initial, that is V1, sorry. V initial is V1, here it is represented, sorry, V1 into e power t minus t1. What is this t minus t1? We already know that this is the time period of the input signal. This is the t1 and this is the t2. If you want the value of t2, just subtract the time period t1 from the total time period. Therefore, total time period minus the duration of the positive section is equal to the t2. That is represented mathematically as t minus t1. Therefore, t means total time period, t1 plus t2 minus t1. So, plus t1 minus t1 cancel by RC. That is equation number 3. Now, at t is equal to t1, that means at the end of the first cycle, the value of the capacitance is V01, that is equal to V1. At t is equal to t1, the value of the capacitance is represented with P1. So apply this condition to this equation. Apply this condition to this equation. That means t is equal to t1, V0 is 1 is equal to V1. Now t is equal to t1, V01 is equal to V1. So therefore V1 is equal to V dash minus V2 into e power minus t by RC. Okay. Next, therefore V1 is equal to V dash. This is V dash term, V dash term. So from these two terms, take V dash as common. Therefore V dash into 1 minus e power minus t1 by RC, minus into minus plus V2 into e power minus t1 by RC. That is represented with equation number 4. Now at t is equal to t1 plus t2, that means at this time, at t is equal to t1 plus t2, V02 is equal to V2. Is it right? V02 is equal to V2. The same V2 is appeared here. Both has the same value. V2 is also equal to V double dash. But while representing, we can notate differently. At t is equal to t2, V02 is equal to V2. Now apply this condition to that equation. Therefore, V02 is equal to V2 and t minus t is equal to t1 plus t2. Therefore, t is equal to t1 plus t2, substitute t1 plus t2 plus t1 minus t1 cancel, therefore minus t2, and V02 is equal to V2. So by substituting this condition to this equation, we can get this. That is V2 is equal to V double dash minus V double dash minus V1 into e power minus T2 by RC. So here also this is V double dash term, this is V double dash term. Take V double dash as common in these two terms. Therefore V double dash into 1 minus e power minus T by T2 by RC plus minus into minus plus V1 into e power minus T2 by RC. That is represented with equation number 5. Now we get the value of V2 in equation number 5. We get the value of V1 equation number 4. So that is this value V2 and V1. V2 this value, V1 this value. Now substitute the value of V2 into equation number 1 because we have V2 term here in equation number 4 that is obtained in equation number 5. Now simply substitute this value into this. Therefore V1 is equal to V dash V1 is equal to V dash into 1 minus e power minus T1 by RC. 1 minus e power minus T1 by RC plus V2 into what is V2? This is the V2 term. That is V double dash into 1 minus e power minus T2 by RC plus V1 into e power minus T2 by RC into e power minus T1 by RC. That is represented here. So if you observe this equation, left side there is a V1 term, right side there is a V1 term. So move all the V1 terms to one side and the remaining terms to right side. So move this V1 term to left side. So take V1 as common. So when V1 is taken as common, 1 minus, because when it 1 minus here, because this is a plus term, moves to left side, we get negative term minus e power minus T2 by RC into e power minus T1 by RC. That means e power minus of T1 plus T2 by RC. Because if you observe this, this term is multiplied with this term. These two are multiplied. E power minus of T1 plus T2 by RC. That is equal to V1 V dash into this term. V dash into 1 minus e power minus T by RC. V double dash into 1 minus e power minus T by RC into this term. E power minus T by T1 by RC. Now move this term to the left side, so to the right side to calculate the value of V1. So whenever you can move that term to the right side, what happened? This whole term divided by this term. That is V1 is equal to V dash into 1 minus e power minus T1 by RC plus V double dash into 1 minus e power minus T2 by RC into e power minus T1 by RC whole by 1 minus e power minus T1 plus T2 by RC. That is represented with equation number 6. Now, if you want to simplify further, then the equation can be simplified as follows. We know that for a symmetrical square waveform, the duration of the positive section and the duration of the negative section are equal. That is T1 is equal to T2 is equal to T by 2, half of the period. Similarly, V1 is equal to minus V2. That means the positive amplitude is equal to the negative amplitude but in opposite polarity. And similarly, V dash is equal to minus V double dash is equal to V by 2. So that is clearly represented here. So T by 2 positive time period is equal to negative time period. Positive amplitude is equal to negative amplitude. Positive value is equal to the negative value. V dash is equal to V double dash. When this happens? When the input signal is a symmetrical waveform. Otherwise that is not valid. Now, if you apply these three conditions to this equation, by applying these three conditions to this equation, therefore V1 is equal to, we know that V dash is equal to V by 2 into 1 minus e power minus T1. What is the value of T1? T by 2 RC minus y minus V double dash is equal to minus V by 2 into 1 minus e power T2. What is T2 here? T by 2 RC whole into e power T1. What is T1? T by 2 RC whole by 1 minus T1 plus T2. that means t by 2 plus t by 2, that is t. T by 2 plus t by 2, that is t, e power minus t by RC. Now, in the numerator, there is a v by 2 term, v by 2 value that is common in both the terms. Take v by 2 as common. Write the remaining equation by multiplying the numerator, we can get this. That is 1 minus v power 2 into e power minus t by 2 RC plus e power minus t by 2 RC whole by 1 minus e power minus t by 2 RC. So this is represented as a square minus 2ab plus b square, and it is nothing but a square minus b square. Now a minus b whole square. So this numerator is represented as a minus b whole square, and the denominator is represented with a plus b into a minus b. So a minus b cancel. So the remaining term is v by 2 into 1 minus e power minus t by 2 RC whole by 1 plus e power minus t by 2 RC. That is represented with equation number 7. If you want to simplify further, take e power minus t by 2 RC as common in numerator as well as the denominator. If you want to simplify further, take e power minus t by 2 RC as common in both numerator and denominator. Then the resultant equation is obtained as v1 is equal to v by 2 into e power t by 2 RC minus 1 by e power t by 2 RC plus 1. If the input waveform is symmetrical waveform, we know that if the input is symmetrical waveform, v1 is equal to minus v2. Therefore, v2 is equal to, here add minus v by 2 into 1 minus e power minus t by 2 RC whole by 1 plus e power minus t by 2 RC, or v2 is equal to minus v by 2 into take e power minus t by 2 RC as common. Therefore, e power t by 2 RC minus 1 by e power t by 2 RC plus 1. So finally, we derived the expressions for v1 and v2 of the output response. So this is the value of v1, that is final charging period, and this is the expression for v2, that means initial charging period. And similarly, v1 is also called as initial discharging voltage, final discharging voltage. v1 is initial discharging voltage, v2 is final discharging voltage, and it can also be called as v2 is initial charging voltage and v1 is final charging voltage. These two values are derived in these two values. If you know the values of t here, t means total time period of the input signal, R and C values are the resistor and capacitors used in the circuit, V is the amplitude of the input signal. If you know these four values, R, C, T and V values, by substituting those values here, you can get the value of V1, and similarly you can get the value of V2. And by using these two values, you can plot the output response very easy. Now, this is about the square wave response. This is about the square wave response of low pass RC circuit for step input signal. Sorry, for square wave input signal. Thank you so much for listening.